Welcome to today's Statistics and Probability lecture. Today we're going to look at 4 easy ways to solve conditional probability problems. Conditional probability is when we have the probability of B given A. So that's the same thing as saying how likely is B to occur given that we already have A. So if I have the probability of eating a cookie given a cookie, that is the same thing as saying how likely is it that I will eat a cookie given that I already have a cookie in my hand. In our first example, we're going to see how to solve conditional probability problems using tree diagrams. Let's look at our first example. This one says, in a bag I have 5 green marbles and 3 red marbles. What is the probability of drawing a second green marble given a green marble was drawn first without replacement? So let's write down what we've been given. We have 5 green marbles and 3 red marbles. So that means I'm going to have a total of 8 marbles. So 8 possible outcomes is going to be my sample space. So that tells me that my probability of drawing a green is going to be 5 out of 8. And the probability of drawing a red is going to be 3 out of 8. Now the problem wants to know what is the probability of drawing a green given a green marble was drawn on the first without replacement. So we'll denote these with a 1 and a 2 to distinguish the first draw and the second draw. This tells us it was drawn without replacement. So this is without replacement, which means these are dependent events. And that tells us that after I draw my first marble, I'm going to leave that marble out, and my total number of outcomes is going to decrease by 1, and whatever color I drew, that is also going to decrease by 1. So let's use a tree diagram to help us solve this conditional probability. On my first draw, I have the possibility of drawing a green at 5 over 8 probability, and I have the possibility of drawing a red at 3 out of 8 probability. Then I'm going to do my second draw, and with each of these I'm going to have the probability of a green or red. So if I draw a green, then my probability is going to be 4 over 7 on my second draw. If I draw a red, my green is going to be a 5 over 7. If I draw a green, then my probability of drawing a red is going to be 3 out of 7. And if I draw a red first, my probability of drawing a red is going to be 2 out of 7. So now that I have my tree diagram to show me how the probabilities are going to flow, let's answer this question of what is the probability of drawing a second green given that I drew a green on the first try. So let's look at this and see what does that mean. What this is saying is that on my first try, I drew a green. So this is what I'm given. And I want to know what is the likelihood that I'm going to draw another green. And that's this probability right here. The probability of drawing a second green when I drew a first is just 4 over 7. And that equals 0.5714, which means that equals 57.14%. There is a 57.14% probability that if I drew a green on my first try, then I will draw a second on my second try. So now let's look at this same problem, but this time we're going to use the formula for getting conditional probability to solve it. Next, we're going to see how to use the formula for conditional probability in combination with tree diagrams to solve for conditional probability. The formula for finding the probability of G2 given G1 is the probability of G1 and G2 divided by the probability of G1. And that equals the probability of G1, G2 divided by the probability of G1, G2 plus the probability of G1, R2. So let's use our tree diagram to help us understand what does that mean and what numbers do we want to use. So let's look at this first one, which is the probability of G1, G2. So that is going to be these two numbers multiplied by each other. So that is going to equal 5/8 times 4/7. Now on the denominator, we are looking at the sample space that includes G. So what that is that is including all of the space right here, all of the probability of G. This is my sample space that includes G. And we're first going to write what we just did, our G1 and G2. So that's going to be 5/8 times 4/7. And then we also need to account for the possibility that if I draw a green one at the first draw, I'm going to draw a red one. So that is this probability. So that is going to be 5/8 times 3/7. And now the next thing we need to do is we just need to do some algebra and move things around to finish solving for our problem. We've got 5/8 times 4/7 on the top. I've got both of my terms are multiplied by a 5/8, so I'm going to use algebra and just pull that out. Combine my like terms, then I've got 4/7 plus 3/7. My 5/8 is on the top is going to cancel out with the 5/8 on the bottom. That gives me 4/7 on the top. 4/7 plus 3/7 equals 7/7, and that simplifies to 1. So 4/7 divided by 1 equals 4/7, which is what we got previously, and then we saw that simplifies to 0.5714, which is 57.14%. So we got the same answer that we did before, that our probability of drawing a green marble on our second try when I was given a green on the first when we used the formula. Okay, let's look at the same problem, but this time let's look at the probability that we are going to draw a green on the second given that we drew a red on the first. So looking at our tree diagram, it's going to be the exact same that we did on the last problem, but this time we are going to draw a red first, and then we want to know what is the likelihood that if I draw a red first, that I'm going to draw a green. And that's my probability. So the probability of drawing a green if I draw a red first is going to be 5 out of 7. And that equals 0.7143, which equals 71.43%. So I have a 71.43% probability that I will choose a green given that I chose a red first. Now let's solve this problem using the formula. So I want to solve for the probability that I will draw a green on the second try given that I drew a red on the first. So that is the probability of drawing a red and a green divided by the probability of drawing a red. And that is the probability of drawing a red-green divided by the probability of drawing a red-green plus the probability of drawing a red-red. So once again, let's visually look at the sample space so we can see what is it that we are drawing, or what is it that we're calculating. So the first thing that we're looking at is we want to draw a red and then a green. So that is this right here. So we're going to put those numbers on the top. So that's going to be 3, 8 for my red and 5, 7 for the bottom for my green. And then this bottom number, the denominator, that is the sample space for drawing a red. And that includes everything in here. So we're first going to write down the probability of drawing a red and then a green. And then we want the probability of drawing 2 reds. Then once again, we're going to use algebra just to move things around to help us to simplify. The denominators are both multiplied by a 3/8, so I can pull that out. Combined terms, my 3/8 on the top cancels out the 3/8 on the bottom. It gives me 5/7. 5/7 plus 2/7 equals 7/7, and that simplifies to 1. give me a probability of 5/7, which is what we calculated before, and that calculates to 0.7143, which equals 71.43%. So that tells me I have a 71.43% that if I draw a red on the first draw, that I have a 71.43% probability that if I'm given a red marble on the first draw, that I will be able to draw a green on the second draw. So this is how we do conditional probability using Venn, using tree diagrams. Next, we will look at how to use contingency tables to solve for conditional probability. In this example, we're going to use contingency tables to solve conditional probability problems. Let's begin by reviewing the formula for conditional probability, and that's the probability of B given A equals the probability of A and B divided by the probability of A. And if you recall, the probability of A and B is the intersection of the two probabilities. So let's solve our first problem. The first problem says find the probability of depression given they are overweight. So that means we want the probability that someone is depressed given that they are overweight. So with contingency tables, I'm going to start with the denominator. The denominator is going to be the probability of being overweight. So let's put this right here. So we're looking for the probability of the intersection of depressed and the intersection of overweight divided by the probability of overweight. So we're going to do the denominator first. So I'm first going to look for my overweight category because that's my denominator. And because I want the probability of overweight, I want to find all of the participants that met that criteria. So that's going to be this right here. So I'm going to put 135 as my denominator. That's the probability of participants that were overweight. The next thing I want is I want to look at, to find the intersection between depressed and overweight. So I've already got my overweight participants, and now I want to look at my depressed participants. And what I'm looking for is where is the intersection between depressed and overweight. And I see that it's right here at 85. That's where the yellow and the green crosses. So that's my intersection, and I'm going to put that right here at the top. So 85 divided by 135 is going to be my solution. And when I do that calculation, that gives me 0.6296, which means there is a 62.96% probability that if my participant is overweight, then they are also likely, they have a 62.96% probability that they will also be depressed. So let's do this same thing with our next question. The next question says, find the probability of being overweight given that they are depressed. So this is asking for just the reverse probability. We want the probability that someone is going to be overweight given that they've identified as being depressed. So that is the probability of overweight intersecting the probability of depressed, all divided by the probability of being depressed. So I'm going to want to find my denominator first. So I'm looking for the depressed participants, and I want to get all of the depressed, the probability of all of the depressed participants. So that is going to be 160. And that's going to be my denominator, probability of depressed. Now I'm going to look for the overweight participants, and I'm going to be looking for that intersection. The intersection where the two colors cross, once again, it's going to be 85. So that's going to be on my numerator. And then when I do my calculation, 85 divided by 160 is going to be 0.53125, which means that I'm going to have a 53.13% probability that if someone has identified themselves as depressed, they are also going to, I have a 53.13% probability that they are also going to be overweight. So you'll notice that on these two diagrams, we were both dealing with overweight and depression, the probability of overweight and depression, but we were reversing our conditions, and so that also reversed the order and gave us slightly different numbers. Let's do two more examples with these same contingency tables. So the next question says, find the probability of depression given they are not overweight. So we are looking for the probability of depression, the probability that they are depressed given that they are not overweight. So once again, our numerator is going to be the intersection of depressed and not overweight, divided by the probability of not overweight. Okay. And let's see what that is. So first I am going to look for the probability of not overweight. So that is this right here. And we want, this is our denominator, the probability, so we want the total number of participants who are not overweight. And that's going to be 100. And then for our numerator, we want the intersection between depressed and not overweight. So that's going to be where these two colors meet, and that's going to be 75. So that is 0.75, which tells me I have a 75% probability that if someone is not overweight, they are 75% likely that they will also be depressed. Let's do our next problem. The next problem gives us the probability of, find the probability of not being overweight given that they are not depressed. So that is going to be the intersection of the probability of not overweight and not depressed. All divided by the probability of not depressed. So once again, I'm going to do the denominator first, and I'm going to look for all of the people who have identified as not being depressed. And so that total, the total number of participants that said they weren't depressed is going to be 75. Then I'm going to find the number of participants that identified as being not overweight, and I'm going to be looking for the intersection of where the not depressed and not overweight so that gives me 25 divided by 75, which is 0.3333, which is 33.33%. So that tells me if someone identifies as not being depressed, there is a 33.33% they will also identify as not being overweight. And in our final examples, we'll see how to use Venn diagrams to solve conditional probability problems. Let's look at this conditional probability example. 300 students are enrolled at the university. 200 students are enrolled in English, 100 students are enrolled in math, and 50 students are enrolled in both English and math. What is the probability of being enrolled in English given the student is enrolled in math? We can use a Venn diagram to help us solve this problem. So let's first fill in the circles of our Venn diagram. We have 200 students are enrolled in English. So let's put our 200 English students and label this yellow circle English. Then we have blue, we have 100 students that are enrolled in math. So we'll put 100 and label the blue circle math. And then we have this green intersection for the students that are enrolled in both math and English. And we see that we have 50 students enrolled in both English and math. So that's going to be 50. So we want to know what is the probability of being enrolled in English given the student is enrolled in math. So before we solve that, let's just look at the probability of each of these events. So the probability of English is going to be our 200 that we have here in the yellow divided by our 300 total students. And that can simplify to 2/3. Our probability of being enrolled in math is going to be 100 divided by the total number of students. So we're going to take the number of the element, divide it by the total number, so that's going to give me 1/3. And the probability of being enrolled in both math and English we can see is this intersection, so we can take that 50 and divide it by the total number of students. So I should have the 300 down here to designate my 300 students. And that's going to simplify to 1/6. So now I want to get the probability of being enrolled in English given that the student is enrolled in math. So let's take a look at that formula, and then we'll see how to solve it with the Venn diagram. So if I'm looking at the formula of being enrolled in English, given that I'm already enrolled in math, that is going to be the probability of being enrolled in math and English divided by the probability of being enrolled in math. So we can see from the numbers that we did before, that is going to be the probability of math and English is 50/300, and the probability of math is 100/300. Then we can simplify that to 50/100, which is 5/10, which equals 1/2, or 50%. Now, if you'll notice on your Venn diagram, we can do the same thing using the Venn diagram, where we take let's write this down, English given math. We have our formula, the probability of math and English, so that's the intersection, so we can just go ahead and get this 50 that's here in the intersection and divide it by the probability of the math, which is the blue. And then once again, that is going to simplify to 1/2, which is 50%. So now that we have identified that if a student is enrolled in math, then there is a 50% probability that they will be enrolled in English. Or another way of saying that is The probability of being enrolled in English, given the student is enrolled in math, is a 50% probability. So now let's reverse those conditions and find out what is the probability of being enrolled in math given the student is enrolled in English. And we'll use our Venn diagram to help set that problem up. So this problem is going to look like the probability of math given they are enrolled in English. So once again, that is the probability of math and English, or being enrolled in both classes, divided by the probability of being enrolled in our English class. So looking at the Venn diagram, we're going to take that green area where they intersect and divide it by the probability of the English, which is our yellow circle of 200. That's going to give me 5/20, which simplifies to 1/4. Which is 25%. So from these two examples, you can see that we can use Venn diagrams to simplify the amount of math and the amount of calculations that we have to do. You just want to put the information that is in each of your problems into the appropriate circles or intersections, and then from there you do the ratios of whatever it is that you're solving for. So just to review, this first one, we had the probability of being enrolled in English given math. So we took the probability of the intersection where we have both math and English, which was the 50, that's in my green intersection, and divided it by the probability of being enrolled in math, which was 100, which is in my blue circle. And that gave me a 50% probability that if a student is enrolled in math, they will also be enrolled in English. For my second problem, we took the probability of being enrolled in both math and English, which is 50, and then divided it by the probability of being enrolled in English, which is in my yellow circle of 200. That gave me a 25% probability that if a student is enrolled in English, then they will also be enrolled in math, 25%. Let's look at the next problem. On this one, it says on a college campus, 75% of the students own a laptop and 65% of the students own a computer. Of the laptop owners, 25% also own a computer. If a student is chosen at random, find the following probabilities. The probability of owning a laptop, the probability of owning a computer, the probability of owning a laptop and computer, the probability of owning a laptop given that you already own a computer, and the probability that you own a computer given that you already own a laptop. For this problem, we can also use a Venn diagram to help us solve it. You'll notice that it's similar to our previous problem, except for that with our previous problem, they gave us data numbers for each of the events, and this time they're giving us the probability percentages. So let's see how that changes our problem. The first thing we're looking at is we want to find the probability of the number of students that own a laptop. So that's right here. It says 75% of the students own a laptop. So that's going to answer our first question. What is the probability of owning a laptop? And we're going to go ahead and put that right here in our yellow circle and label that laptop. Our next question is, what is the probability of owning a computer? And the problem tells us that 65% of the students own a computer. So that answers our second question about the probability of owning a computer is 65%. We're going to put our 65% in the blue circle and label the blue circle computer. Now the next question says, what is the probability of owning a laptop and a computer? And that's going to be this green intersection where our two circles intersect, the intersection between owning a laptop and a computer. And we can see the problem says of the laptop owners, 25% also own a computer. Now this one, the way that it's worded is a little tricky, that if you're not paying attention, you're going to think that that intersection is 25%. But what that problem is telling us is that 25% of the laptop owners own a computer. So this is the intersection is not 25%, it's going to be 25% multiplied by the 75% of the laptop owners. So that's going to be 0.25 times 0.75. And that's going to give me 0.1875, which is 18.75%. So the probability of owning both a laptop and a computer is going to be 18.75%. So I'm going to put that here in the intersection, in my green intersection. So that's going to make solving my conditional problems a lot easier because now I've put my numbers into my Venn diagram. And if you'll recall, when I'm doing a conditional probability, I'm looking for the probability of the laptop and the computer divided by the probability of the computer. So that's going to be the intersection of the laptop and the computer, and that is 18.75% divided by the probability of the computer, which is 65%. I'm going to change those to decimals so I can do the math. And that is going to give me a 0.2885. So that means I have a 28.85% probability that if a student owns a computer, then they will also have they'll have a 28.85% of also owning a laptop. And our last problem wants to know the probability of, given that we have a laptop, what is the probability that we will have a computer? So that is the probability of the computer and laptop divided by the probability of the laptop, which is going to give me that intersection that's in the green, divided by 75%. I'm going to change those to decimals. Which is going to give me 25%. Now, if you'll notice, our problem initially told us that of the laptop owners, 25% also own a computer. So that is another way of saying that given that we have a laptop, 25%, there's a 25% probability that they're going to have a computer. So in this problem, instead of giving us the intersection, they gave us the probability, the conditional probability of having a computer given that you already had a laptop. To summarize, there are 4 easy ways to solve conditional probability problems: using tree diagrams, using the conditional probability formula in combination with tree diagrams, contingency tables, and Venn diagrams. I hope you have found this tutorial helpful. See the links below for additional supports and resources, and be sure to like and subscribe to get the latest videos by Caz Academy. I'll see you at the next video. Thanks for watching.